Hi, I'm Adam. This is the Behrend Robotics Club submission for 2023's URC System Acceptance Review video.
When we started designing the gearboxes, we already had our wheel diameter and our motor selected. So from here we could back out the ideal gear ratio of 27:1. And we also knew that we wanted a standard setup gearbox instead of a reverted or a planetary gearbox, so that way we could remove our motor from the ground and get maximum ground clearance. So with this in mind, we started looking for gearboxes, and we saw all the commercially available boxes were just heavy and expensive. So this prompted us to buy gear stock, and we bought a soft steel gear stock so that way we could cut it and machine it to the size we want. Unfortunately, this steel had a low fatigue life and a low strength. So what we did to solve that is once the gears were machined and sized correctly, we case hardened them with a pack carburizing process, which gave us a tough ductile core and a hard exterior to withstand the wearing of the gears. That's what led to our final design of the gearbox, which not only gave us the torque ratio that we wanted and a slim profile with the case hardened, but it also removed the gearbox as far away from the center of the wheel as possible to achieve maximum ground clearance.
A lot of thought went to the wheel design for our rover. We knew we wanted a large wheel that would allow our rover to easily climb the terrain of the desert. We also wanted a wheel that could absorb the impact in case the rover were to fall off a small ledge. Our first wheel design used ABS plastic. This wheel design was 3D printed and is the proper size for our rover. This wheel also does a good job of transmitting the torque from the center shaft to the outside of the wheel. However, when we did an impact test by putting a metal bar through the center of the wheel and then dropping at a half meter with 50 pounds of load, it failed. At this point, we wanted to modify our design for impact. By using ANSYS, we were able to simulate drops from different heights. This led us to believe that our original wheel design needed modified, and our material choice also needed to change. This led us to our second wheel, which uses a concentric hexagon pattern as well as TPU material to allow a large amount of impact resistance as well as conformity to the environment. We're still working out the torque transfer issues with this new wheel, but we plan to use a metal plate to transfer torque from the hex shaft to bolts within the wheel.
For our robotic arm, we chose to use a granular jamming gripper. This type of gripper has a porous material on the inside, and whenever you apply a vacuum to this, it's able to morph around any object that is available to it and then pick it up. Then for our arm, instead of going with bigger motors everywhere, we chose to go with these smaller motors and use a cyclodal drive, which is able to be back driven. It has low backlash, which means that we can better accurately figure out whenever we are in contact with a object, and it gives us a very large torque ratio, which is great for these small motors.
To test for life, we plan to perform enzyme testing on soil samples. We chose to test the enzyme catalase due to the fact that it can be found in all living organisms. After collecting a soil sample, we will add hydrogen peroxide to the test tube. Because the reaction between catalase and hydrogen peroxide is exothermic, if catalase is present in the sample, there will be a measurable change in temperature. The test tubes are stored in a Geneva drive, and once the drive makes a full rotation, the test tubes will be capped to prevent contamination.
For our controls system, we are planning to use an NVIDIA Jetson board powered by ROS2. So far, we've made progress simulating the robot in Gazebo, as well as driving a few of the motors. When it comes to the electrical design of our robot, we realized we need a custom battery pack to power the rover. We're using 21700 lithium cells in conjunction with a BMS to properly provide the current needed to drive all motors on the robot. To contain all of our electronics, we plan to design a sheet metal box that will house all the motor controllers and control electronics. The box will have two sections so that the high noise brushless motors will be separated from the high fidelity wireless communication equipment. Motor control is being done with VESC 6 motor controllers as well as ODrive Pro motor controllers. All the motor controllers will be placed around the outside edge of the box so that their heat can be dissipated to the outside environment.
The Behrend Robotics Club participates in several outreach events. Annually, we teach a robotics-themed Girl Scout badge and volunteer at the first LEGO League competition hosted on campus. This year, we volunteered at a local VEX event and ran a table at a STEAM fair for local elementary school students.